Okay, it's 11:01, so I think I'm going to mute myself and let you all take over.
All right.
All right, I apologize in advance because I'm the host, so you might hear that noise because people are trying to come in. Oh my goodness. Okay, I'll try to ignore it. All right, welcome to the virtual conference for the National Weather Center Research Experiences for Undergraduates program. My name is Alexandra Marmo, and I'm the co-director of the National Weather Center REU program. I run this program with Daphne Ledoux, who was recently voted to receive the Robert H. and Joanne Simpson Mentorship Award by the American Meteorological Society for generous, thoughtful, and caring mentorship to students and their supervisors during more than 20 years of directing the Oklahoma Research Experience for Undergraduates program.
I'm so excited.
The National Weather Center REU program is funded by the National Science Foundation. NSF has been funding REU programs since the 80s. Our NSF funding began in 1991, led by Bill Beasley and others from the School of Meteorology in partnership with NSSL. Since then, we have had over 220 students come through Norman on 8 REU grants. These programs bring bright undergraduates from around the country to join our organizations and see what research is really like. The 12 REU students, all from different universities, have joined us from far as Puerto Rico and California. Unfortunately, we are unable to share a summer together in Norman, but we have grown to know each other through GroupMe messages and Zoom meetings. Our mentors are from 11 different organizations, including OU's CIMMS, ARRC, CAS, and both the School of Meteorology and the Department of Geography and Environmental Sustainability. We also have NOAA's NSSL, NWSFO, WDTD, and GSL, along with the OCS. For our audience today, this conference will be set in the format of AMS annual meetings with a 12-minute presentation followed by a 3-minute Q&A period. Please remain muted and hold all questions till the end of the talk. At that point, we will ask you to send the letter Q in the chat. That way we could keep our questions kind of orderly. To our students, these talks may seem scary, but they're also really exciting. Scientific conferences are a great way to share what you found through your research and get feedback from others in the field. Now I'll hand it over to our moderators, who are Kelsey, Britt, and Elisa Murillo.
Murillo.
I'm sorry.
You're good.
All right, so our first speaker is going to be Melanie Zambron. So Melanie, do you want to go ahead and share your screen and get that started? All right. So Melanie's going to be talking about tornadoes in the Southeast United States, investigating the relationship between intensity, damage, and terrain. Melanie, you can go ahead whenever you're ready.
All right. All right, thank you very much for the introduction. This summer, I am working with Dr. David Bodine and Dr. Anthony Reinhart, and this research was supported by the NSF. So for a little bit of background information, tornado research brings a variety of challenges, including the difficulties that come with forecasting tornadoes, as well as rating intensity, especially when a tornado travels in an area with very little damage indicators. Additionally, some tornadoes can show weak rotation signatures on radar and yet still be very strong tornadoes. Also, there has been minimal research conducted involving complex terrain and its impacts on tornadic circulations. So our research aims to answer 2 questions. Do changes in terrain impact storm scale rotation? And additionally, what contributes to differences in rotation signatures for tornadoes of similar strengths? So previous research has shown in model simulations that even small changes in topography height can impact the strength, structure, and path of a tornado, with the near surface inflow being the most affected part of the tornado. Additionally, valleys can channel winds to even increase the wind speeds outside the main damage track of a tornado and create damage within the valley as well. And with regards to supercells and terrain, the ground relative winds are the most important feature, with whether they are moving upslope or downslope based on the different thermodynamic modifications that would bring, whether that be to the sounding profiles with the SIN or the convective inhibition or the relative humidity, as well as the hodograph shape, as in the wind shear. So we looked at 8 tornadoes for our research. 2 of them came from the 2nd to 3rd of March of earlier this year. One of them was the Nashville EF3, which was on the ground for 63 minutes, traveling just over 60 miles. And the second was the Cookeville EF4 that was on the ground for 8 minutes, traveling just under 8.5 miles. And something interesting to point out here is on the top, we have the start and the end of the Nashville tornado track, and on the bottom is the Cookeville tornado track. And it is interesting to point out that at the beginning of the Nashville tornado and at the end of its track, as well as at the beginning of the Cookeville tornado track, there are areas of significant changes in terrain, whereas throughout the tracks of the tornadoes, there's very little changes in terrain. So it is interesting to note that at both sides of the tornado track. We also had tornadoes from the Easter Sunday outbreak of this year. We had 2 EF4s, the Walt Hall EF4, which was on the ground for 26 minutes, traveling just over 21 miles, and the Bassfield EF4, which was on the ground for 77 minutes, traveling at about 68 miles. And we also had the other long track, Oakville EF3, which was on the ground for 91 minutes at a path length of about 84 miles. Now, with these tornadoes, there was no significant terrain throughout the tornado, as well as on either side of them. We also had the Reese City EF1 and EF2. Now, the EF1 is technically the Miller's Hollow EF1, and it was on the ground for 5 minutes, traveling just about 5.5 miles. And the Reese City EF2 was on the ground for 14 minutes, traveling just about 12 miles. Now, the interesting thing with these tornadoes is that they were separated by about a 1-minute gap, and between them was actually a ridge that created about a 300 to 400 meter difference in height between the ground where the tornadoes were touching down and the top of the ridge. But we did confirm with the National Weather Service in Birmingham that these were in fact 2 separate tornadoes. And finally, we looked at the Chattanooga EF3, which is on the ground for 18 minutes, traveling a path length of about 20 miles. And here again is some more images of the Reese City tornado, where you can see on the left screen, the EF1 is to the left of the ridge and the EF2 is to the right of the ridge, and they travel nearly parallel to the ridge as well. So for our data and methods, we looked at single radar velocities from the Nashville radar, the Jackson radar, and the Huntsville radars. And we also looked at MRMS, or multi-radar, multi-sensor rotation tracks from 0 to 2 kilometers. We looked at the damage surveys for these tornadoes with both the tracks and the ratings. And we also looked at terrain data from the United States Geological Survey, or the USGS. And from the single radar velocities, we recorded the maximum inbound, which is a negative value, and maximum outbound, which is a positive value velocities. And we took the absolute value of these two velocities at each time step and added them together to get a value called delta V, which essentially shows rotational intensity. And we did this at the lowest 3 to 4 elevation scans that were available on our radars. And since we had the 0.5 degree scan for each radar, we recorded at those same time steps the maximum rotation tracks value, the terrain height, and calculated the damage width from the damage surveys. And a little bit more on the MRMS rotation tracks product. The MRMS system essentially blends all of the NexRad radars into one display. It is operationally available and consists of a variety of products that update every 2 minutes on a 1 kilometer grid. And the rotation tracks product actually plots the highest azimuthal shear, or shear between consecutive directions around the radar, over a certain time interval, showing rotation at a point. And on the left side of the screen, you can see one example of a rotation tracks product for the Nashville tornado. So for our results, we looked at 6 different variables. We looked at delta V, the damage width, the maximum EF rating, the terrain height, the velocity couplet width, and the maximum rotation tracks. Now there's an asterisk on the velocity couplet width, just as a side note that I'm using that term a little bit loosely for some of our cases, whereas sometimes our minimum and maximum values were about 10 kilometers apart, and that was more so near the end of the tornado tracks, especially higher up in the atmosphere. So I'm just loosely using that term. Most of the time it applies, but at some points it's a little not exactly that. But on the graph, you can see our 6 tornado cases and all of our variables. We calculated correlation coefficients between those, and I circled the ones that are the most correlated, as well as ones that seem to be a bit different than the other cases. And I will go into a little bit of detail about these. For the Nashville case, the Nashville tornado was the closest to its radar. So this one, we actually were seeing the beam height below 1 kilometer. So we're seeing the tornado level winds with this. However, we still saw very little correlation to terrain with these variables, with the highest correlation coefficient being about 0.26 between delta V and the terrain. And terrain compared to all the other variables showed a lot less of a correlation than that. But take note that the Nashville tornado was about an hour long, but because of a lot of data artifacts in the first half hour, we decided to only take data from the second half hour of the storm. And for the Cookeville tornado, this one happened right after the Nashville tornado. So at this point, we're at a bit of a further range from the radar. So our beam height is going to be higher above ground level. So for this tornado, our radar was scanning more in the mesocyclone level. And the Cookeville tornado was also a lot shorter. So we see some differences compared to the other cases in this one, specifically with the maximum EF rating and the delta V correlation. This correlation is actually a lot lower than compared to the other cases. And additionally, the correlation between maximum EF and maximum rotation tracks actually showed a negative sign, whereas opposed to the other cases, which had a positive correlation between these two variables. Now, a little more on Nashville and Cookeville. As I said, the Nashville tornado was a lot longer than the Cookeville tornado, but it was weaker. And that's only on the scale of about EF3 to EF4. So they were both still strong tornadoes, but the Cookeville was a bit stronger as an EF4. And the Cookeville tornado was farther from the radar. And therefore, it looked weaker on radar because the radar beam was actually scanning higher, more into the mesocyclone scale winds, and less representative of the low-level winds. The Cookeville tornado, however, did have a very strong TDS, or tornado debris signature, as you can see on the right in the correlation coefficient plot, with the lower values inside the circle along the track of the Cookeville tornado. So for the Walthall and Bassfield EF4 tornadoes, note the purple box on the graphs that indicates the break between these two tornadoes, which is about a 7-minute gap where neither the tornadoes were touching on the ground. And on the damage width and max EF rating graph on the right, that green bar indicates that for the Bassfield tornado, we were not able to get an EF0 damage contour. So our damage width is actually for the EF1 contour, whereas for all of our other cases, the damage width is for the EF0 contour. Now for this tornado, we were at a further range from the radar, and thus our beam height is going to be higher. So we're more in the mesocyclone level in this one. But we're still seeing very little correlation to terrain, with the highest correlation coefficient being between terrain and the max rotation track value at about 0.25, and all the other variables showing less of a correlation to terrain. And the Oakville tornado is actually incredibly similar to this one in its correlation coefficients, which is really interesting. These tornadoes were separated by about 10 miles and about 30 minutes apart, and they were from two separate supercells, but their characteristics were incredibly similar. And for Erie City tornado, also note the box there indicating that 1-minute gap between these two tornadoes. And again, we're seeing a farther range from the radar, and our beam height then is going to be higher. We're even seeing above 2 kilometers with this case. So we're really into the mesocyclone level. And again, we're seeing actually weaker correlations within this case as opposed to the others where, especially in delta V and the max EF rating, the correlation between those is very low and opposite in sign compared to those two variables with the other cases. And finally, the Chattanooga tornado was also at a farther range. So we're seeing more in the mesocyclone level, even above 2 kilometers in some of the cases. But if you note on these graphs, our intensity and damage are actually very well correlated with one another. However, we are still seeing that weak correlation to terrain, with the correlation coefficient between terrain and delta V being about 0.36, and all the other variables showing an even less correlation than that. So to kind of compare these in a little more graphical way, our terrain height correlations are shown on the left with each of the variables, and on the right is our delta V correlations with our other variables. And we broke these down into 3 categories, in which we classified weak as having a correlation coefficient of 0.3 or less, moderate having 0.3 to 0.7, and strong having either equal to or greater than 0.7. Now, the interesting thing to note here is in the terrain height correlations, none of the variables showed a strong correlation with terrain. There were some in the moderate section, but mostly in the weak for this with terrain. And with delta V, we are seeing more in the strong section, especially even more in the moderate. But it's really interesting to note that for terrain, we saw no strong correlations with any of the variables. Now, we did see some moderate with delta V, max rotation track, and couplet width, but however, none of these are including the Nashville tornado. So remember, Nashville was our lowest scan that we were able to see. So the delta V in all these cases were actually only comparing to the mesocyclone. So the terrain correlated better to the mesocyclone. And our damage width and max EF rating only showed weak correlations to terrain. So to sum that up a little bit, our intensity variables showed some moderate correlation to terrain, whereas our damage variables showed very weak correlation to terrain. And with delta V, again, as I mentioned, note all except the Nashville tornado are measuring velocities at the mesocyclone level. We're not actually seeing the tornado itself. Yet we did see more strong to moderate correlations than with the terrain variables. And our best correlated with delta V was the max rotation track, with 3 in the strong category and 2 in the moderate. The maximum EF rating had 2 in the strong, 2 in the moderate, and 2 in the weak as well. Now I'm going to flip back real quick and note in the delta V correlations that the damage width and couplet width had only 1 in the strong category. And that was actually both the Nashville tornado. So that shows that the Nashville tornado had really good correlation between delta V and the damage width and couplet width. So to summarize our study, we looked at the correlation among radar velocities, terrain, and surface damage. Additionally, we took note that some tornado formation locations came out of rougher terrain, especially with the Nashville, Cookeville, and Reese City tornadoes. But with those ones, we really only focused on taking data over the tornado track, so we did not record values outside of those. But it is still interesting to note that that terrain was there. And additionally, very important in the study is the limitations of the radar. As you get further from the radar, your beam height is going to be higher. So it's really important to take note of whether we were looking at the tornado scale winds, which was only in the Nashville case in our study, or the mesocyclone scale winds. And for the stronger tornadoes, we had the EF3 and EF4 tornadoes. The maximum EF rating and delta V were very well correlated, with the exception of Cookeville having a very weak correlation due to its small diameter and short duration being only an 8-minute tornado. And lastly, our Nashville tornado, which again was our best example of low-level winds, it was the closest to the ground that the NEXRAD could measure. With regards to our cases, we still only saw a very low correlation to the delta V rotational intensity and the terrain. So that is all I have. Any questions?
Awesome. Thank you, Melanie. I'm going to go ahead and give her a round of applause so she can hear it. And if you have a question, go ahead and type a Q in the chat, and I'll cue you to, unintended, to unmute yourself when you have a question. We have people saying great job and applause, of course.
Thank you.
In the meantime, while we wait for some other questions, I did have one quick question. How did you choose which tornadoes to include in this study?
More so just more recent ones and cases that had a lot of them. I guess there wasn't really much of a specific way that we chose them, but they were recent and in a lot of people's memories at this point. So,
yeah, that makes sense. Awesome. Yes, you're getting lots of great feedback in the chat, which is what's great about this opportunity. All right, go ahead and unmute yourself, Harold. Harold Brooks has a question.
Okay, and I hope the microphone's working. The question is, are there any other variables you could think about that you could try to correlate with? And there's sort of this underlying question of, okay, you get a correlation coefficient of X. Is that a really big number, or is there some other variable in the area that you could have used to compare with? And I have no idea what the answer to that is.
I'm sure there are others that we could have correlated with. This seemed to be the best for what we were working with, so that's what we decided to focus on for our study. But I'm sure there are other ways that could be used to compare with it as well.
Okay. Thank you.
Yeah.
Awesome. All right. Well, we have another question from Sam. Go ahead and unmute yourself, Sam.
All right. Can you hear me?
Yes.
Mm-hmm.
Okay. So my question is, looking at these different cases, I think at least some of the different radars, I think DGX with the Bassfield and Walthall tornadoes, I think they had differing sales modes and obviously like differing elevations as well. Do you think the different modes of scanning may have affected the actual delta V measurements? Whereas with sales, you have more low-level scans, so you're getting essentially sampling more points along the tornado track. Do you think that would have made a significant difference in some of these tornadoes, just in your experience?
I don't really think so. So for all of them except the Walthall and Bassfield and Oakville tornadoes, they were using sales on the 0.5 scan, so we were getting updates about every 1.5 to 2 minutes on those ones. So we had delta Vs for those that frequently for that level. But with those 3 tornadoes in Mississippi, they were using the sales on the 0.3 scan. So our 0.5 actually updated about every 6 minutes. So in that case, it probably would have, helped to have the sales on the 0.5 scan to be able to compare all together. But they had them on the 0.3 scan. But since the other radars did not have that low of a elevation scan, we decided just to take note of that and record it, but not really include it in the full discussion.
Okay. Thank you. Great talk.
All right, let's go ahead and give her another round of applause. Great, thank you so much. And I'll go ahead and turn it over to Kelsey to move on to our next speaker.
All right, so our next speaker is going to be Neil Crosby. So Neil, can you go ahead and share your screen?
All right, it should be coming up soon.
Okay. So Neil's actually going to be talking about the effects of extratropical transition on tornado production and hurricanes. So whenever we get his presentation up. There we go.
Okay, you can see it?
We do see your screen.
Okay. All right. Oh, come on.
There you go. Whenever you're ready.
Right. Yeah, thanks. All right, so my name's Neil Crosby. I'm in collaboration with Ben Schenkel on behalf of OU School of Meteorology, CIMMS, and the National Science Foundation. And we're going to be discussing our research on the effects of extratropical transition on tornado production and hurricanes. Okay. So I think it should be appropriate to start off with some motivation for the research. And I just want to bring up just some quick points. First, the first one is that tropical cyclone and cyclone tornado production in general is not widely understood. I mean, there's literature, but there's, of course, some knowledge gaps. And these knowledge gaps, of course, will make forecasting more difficult for forecasters and like issuing warnings and stuff like that. So that's where I believe this study will come in handy in laying some groundwork for understanding these tornado environments more. So a fact about TCs is that about 50% of them undergo extratropical transition in the Atlantic. And with that being said, I just want to bring your attention to this figure on the right really quick. All right, so this is a track of Hurricane Ivan, which also, by the way, is one of the biggest tornado producing TCs in recorded history. So it started out in the Gulf of Mexico, made landfall, as you can see, in the Florida Peninsula, moved through Alabama, Northwest Georgia. And what I want to draw your attention to is these cluster of red triangles, which is tornado reports. So as you can see by the color key, and we're discussing extratropical transition, you can see the green, where these tornadoes occur is right where the green transitions to blue, which is extratropical. So it's interesting just to note that this many tornadoes occurred in this region. So, and that raises the question, which we might be able to answer with our research: does extratropical transition change tornado frequency and location? All right. So now, having gone over the motivation, you might ask the question: why is extratropical transition important? So we can first start off by defining this as the process by which a hurricane or a tropical cyclone becomes a mid-latitude cyclone, and it it causes distinct structural changes during this phase. And I just want to note that we're going to refer to the extratropical transition as a phase, not as a separate entity. So it's all a part of the cyclone lash cycle. So it causes structural changes, and it causes the structure to weaken and become asymmetric. And prior work has yet to study the effect, as we stated, as we discussed in the last slide. So this figure, starting out with the figure on the left, is Hurricane Sandy before transition. And as you can see, contrasting the two, these are infrared satellite images. And as you can see, the figure on the left, it represents Hurricane Sandy before transition. You can see it's more symmetric, has increased convection, all these things that would classify, would characterize a tropical cyclone. And extratropical Hurricane Sandy during transition, of course, is, you can see that there's much less convection and it's much more asymmetric. So these are the structural changes. But of course, even though it's weaker, it still has the potential for tornadoes. So we'll look at that further. All right. So now we can ask the question, now that we've covered the motivation and why the extratropical transition process is important, we can ask the question, how can it be classified? So an objective way of defining this process is by using the cyclone phase space. And it's very simple. We simplified it to a tool which uses two parameters, frontal zone strength and cyclone type. And the degree of these will determine whether the storm is extratropical or tropical. So with frontal zone strength, the storm can have a strong temperature gradient, or it can have it doesn't have a strong temperature gradient. So if it has a strong temperature gradient, it's usually going to be frontal, which is characteristic of extratropical cyclones, as you can see on the figure to the right. And a tropical cyclone would usually be non-frontal and would not have a temperature gradient. And moving on to cyclone type, it determines where the winds are strongest. So cold core cyclones are usually extratropical as well, and they have winds that increase with height. And warm core cyclones have winds that decrease with height. So just to sum this up, extratropical cyclones are usually frontal and cold core. Tropical cyclones are usually non-frontal and warm core. So these are the distinguishing parameters. So that brings us to the question, how do these specific structural changes impact tornado occurrence? All right. So with that question in mind, our objective is simply, and there's a lot of text on this slide. I'm just going to walk you through it. Bear with me. So our objective is to investigate differences in tornado frequency and location between both the phases, tropical and extratropical transition. And we're going to do this by using National Hurricane Center track data. It provides 6-hour track data and intensity data from 1995 to 2019 over 192 landfalling TCs. And the Storm Prediction Center TC tornado data, which provides TC tornado and damage, track and damage from 1995 to 2019 and over 1,352 tornadoes. And of course, the cyclone phase space, which defines extratropical transition. We're going to be using atmospheric reanalysis data, which is basically a simulation of past weather events that includes observations. And the start and end times, of course, the start time is going to be defined by how strong the development of the strong temperature gradient in the lower troposphere. And the end is going to be classified by the transition from warm to cold core. Okay. So with the research question in mind, how does extratropical transition affect tornado location and frequency? I want to bring your attention to our first set of results that basically describe differences in tornado frequency. So this graph that we generated, it it represents the total number of cases for tropical and extratropical phase, and the number of tornadoes per 6 hours for each case, and the percentage of those cases. So the tornado number is for a baseline. I just want to note that it's typically around 0 to 1 for both cases. And more tornadoes, this is a defining one for extratropical lands. The transition, more tornadoes per given 6 hours for these cases, as you can see on the graph. So as you can see by the bends here. And if you're confused by this y-axis is just a log scale, it basically accounts for the smaller percentages. So extratropical transition cases are also associated with higher end tornado events, like upwards of 30, as you can see by this bend right here. Okay, so moving on to tornado location, our results for extratropical transition are right here. So you can see, as you can see, this is a gridded map plot, and it shows the relative location and number of tornadoes for extratropical transition. So what we found is these tornadoes were generally confined to the East Coast. And as you can see, there's a concentration of 20 or so tornadoes in these regions around Georgia and Virginia. And we're going to move on to the contrast. So starting off, I just want to know there is a significant number of TC tornadoes that occurred during extratropical transition. So that's pretty noteworthy, 28%. So what we found is most extratropical transition tornadoes are much farther east than tropical phase tornadoes. And extratropical transition are maximized in the mid-Atlantic. So overall, we can see that the location is significantly altered with extratropical transition. All right. Oops. All right, so distance between tornado from TC center. These are our results for the distance for storm center for each case for extratropical transition and tropical phase of cyclones. So we did not find a substantial difference, basically. So as you can see, tropical phase tornadoes are more likely to occur within 200 to 400 kilometers. Extratropical transition is likely to occur for 100 to 500 kilometers. So there's really no difference. And the small difference could be due to the asymmetrical structure of extratropical cyclones. All right, so conclusion. Larger percentage of 6-hour times for extratropical transition cases produce tornadoes. Okay, this is a short period of time that the extratropical transition alters the frequency, and extratropical transition tornadoes are confined to the East Coast, while tropical phase tornadoes are broadly over the southern U.S. And small differences, of course, in the distance from tornadoes from the cyclone center. And overall, these results suggest that extratropical transition does affect tornado production. All right. So thank you for your time. Are there any questions?
Yay! So let's go ahead and give Neil a round of applause. Did a great job. If you have a question, go ahead and type a Q into the chat. And all right, we have a question from David. Go ahead and unmute yourself.
Hi, Neil. Great job. I have more of a thought question. So do you think there's any effect on tornado intensity, like for tropical versus extratropical events?
That's actually a good question. So in our paper, we actually did generate a graph of the intensity. So we did find small changes, but it was very minimal, like around the F2 damage rating. Yeah, so there's really no difference in intensity. I appreciate it.
Thanks.
All right, Ben, did you want to chime in? You seemed very excited by that question, so I just wanted to give you the opportunity to chime in there.
No. I think Neil did it justice. There's not really big differences.
Perfect. Yeah, awesome. We have a question from Brian. Go ahead and unmute yourself.
Okay, good. You muted yourself. Great job, Neil. This is really cool work, important stuff. Just a quick question about those maps towards the end of your slides with that had like the spatial frequency. Do you know how those would change if you played with the grid spacing a little bit? Because I noticed on Florida there were only like 4 or 5 boxes. I'm sure if I lived in Miami, I might be like, Just wondering, that's all.
You said if you change the dimensions or something?
If you made the boxes a little bit smaller, would you still get those big hot spots like in the center of Florida, or would they maybe be along the coast a little bit more? Do you have a sense of that?
That's a good question.
I'm not sure if I'm wording the question.
Sorry. Thank you. Sorry, we're in the same room, so sorry if y'all heard some echoing. So you said you weren't really sure, which is totally fine. Did Ben want to follow up on that? Once again, give you the opportunity if you knew the answer, and if not, once again, totally okay.
I think like Neil, we're not completely sure. This is like sort of our first hack at that, but it's definitely something we should look into just to see what the sensitivity of the results are to the size of the boxes. So I think Neil was good on his first assessment there. We need to look into that.
Yes, I agree. I think that's pretty cool.
Thank you.
Well, great. Let's go ahead and give Neil another round of applause. You did awesome. All right. So I'm going to go ahead and turn it over to Kelsey to introduce our next speaker. Everybody's doing so great. This is awesome.
All right, so our next speaker is America Gaviria. You can go ahead and share your screen if you like. She will be talking about understanding the correlation between NWS impact-based /flood warning categories and various NWS /flood tools. All right, and you can go ahead whenever you're ready.
Okay, thank you so much for the introduction. This summer I was working with Jill Hardy, Dr. Jonathan J. Gourley, and Todd Lindley, and this project was funded by the NSF. So a little bit of background. First of all, what is a flash flood warning? So if a flash flood warning is issued when an overflow or inundation event is occurring with a rapid rise of stage that threatens life and property. So here's an example of a flash flood warning text product from the National Weather Service. So you can see that it has the date and the time, it has the hazard, the source, the impact, and the locations that will be experiencing the flooding. So what are impact-based warnings? So recently, the National Weather Service started issuing impact-based flash flood warnings in order to add stronger language to the warning based on the impacts that are possible or occurring. So currently, we have 3 categories for these flash flood warnings. These are base, conceivable, and catastrophic. So the conceivable and catastrophic categories, they both activate the wireless emergency alerts that go on your devices when these events are occurring. So a base event, this category is used most of the time when flash flood impact damage is possible. So some of the keywords we can find in this category are heavy rain, any or center language, or a generic call to action. So here's a picture of what a base event would look like. So you can see there's a little bit of water over the road. It's like a country road, and there is a little bit of flooding over the yard. So it's not that dangerous of an event. So next we have the considerable category. This one is used rarely when there are indications flash flooding capable of unusual severity impact is imminent or ongoing, and urgent action is needed to protect lives and property. So some keywords we can find here are evacuations like water rescues or vehicle stranded. So you can see in the picture that this is more of a widespread flooding unlike the last one, so it is a more dangerous situation. And lastly, we have the catastrophic category. So this category equals a flash flood emergency. And this one is used exceedingly rare when a flash flood threat to life and catastrophic damage is occurring or is imminent, and floodwaters have risen or will rise to levels rarely if ever seen. So some keywords we can find here are multiple water rescues, home destroys, and life-threatening situations. So in the picture, you can see this was from Hurricane Maria. You can see that a lot of houses are flooded and destroyed because of the water, and the water is a police use. So this is definitely a flash flood emergency. So the data from this project that we used was from the National Weather Service from data, and the flash flood reports came from the Weather Forecast Office in Norman, and they were from 2013 to 2019. We also used some tools from the Iowa Environmental Methodist. These were the local storm reports and the Iowa Environmental CAL, a storm-based warning verification. We also used reports from social media such as Facebook, Twitter posts, YouTube videos, news articles, and event summaries to support the reports we already had. So the methodology for my project was to classify the database of the recent flash flood events based on their perceived impact-based categories. So we had a total of 671 events. So, but for example, in a particular day, we could have had, for example, like 7 events happening. So out of those 7 events, we took the daily max of those events during that particular day. So after doing that, the events narrowed down to 141 events. So after this, we performed a statistical analysis to determine the distribution of the flash flood events based on their impact. So we wanted to know what percentage of the events would be base, the percentage of the events that would be considerable, and the percentage of the events that would be catastrophic. So in this chart, you can see the events per year. So you can see that in 2015 and 2016 occurred the majority of the events, with 28 events occurring in both years. And you can see that in 2014 had the less amount of events, with only 6 events happening during that year. Then we have the events per season. So you can see that during the spring and summer season occurred the majority of the events, with 59 and 60 events respectively. And during the winter season, there were only 2 events reported. So basically, there were not many events during that season. And this was for the 141 events. So this is an example of what I was actually doing to classify the events. So this was the report from the storm data, and you can see this has the location of the event, the part is in red. It has the death and injuries, the property and crop damage, and event type of details. So it has the cause of the event, that was heavy rain, and it is important to know that the cause for all of the events was heavy rain. So we analyzed just the events based on the heavy rain, and the source. And here's a brief description of the event. So this description says that several vehicles were partially submerged in flood waters, and 5 individuals seeking shelter in a drainage ditch were swept away and killed, damage estimated. So from this description, we took away some keywords that could let us to classify the event as based considerable or catastrophic. So in this particular case, we used submerged, swept away, and killed. And also we look at pictures on social media, and you can see that the vehicles are submerged, and it's definitely a catastrophic situation because it's life-threatening. So we ended up classifying this event as catastrophic. So like I mentioned before, we use keywords from the reports. So here's a table that shows the most common keywords for each category used. So you can see that the base category, the most common keywords were water over highway and closed. And when I say closed, I mean roads closed or highways closed. For the considerable category, vehicles stranded and water wrecked were the most common ones. And for the catastrophic, killed and closed as well, but closed meaning interstate closed were the most common keywords for these categories. So something you would notice is that in the 3 categories, some of the keywords are repeated. And this is because sometimes one keyword could fit into the 3 categories, and that could create a level of uncertainty when classifying the events, and it was kind of a struggle to classify those events. So for example, if I say water over highway, you could picture, you can come up with some different things in your mind. So you could come up with any of these 3 images, and they 3 would mean water over highway, and they 3 would fit in the 3 categories. So this was kind of a struggle in classifying the events. So this is why we classified the events twice. So for the first time we classified the events, we used a specific keyword for the considerable category, and then the second time we used that same keyword but for the base category. So the keyword was roads closed. So the first time we classified the events using the keyword roads closed for considerable, we came up with 62% of the events being considerable and only 19% of the events being base. After we did the reclassification, the considerable was still the category with the most events, but it was only 47% compared to the first time, and then the base was 35% compared to the first time that it was way low than 35. So yeah, this creates a level of uncertainty when classifying the events, and it's kind of like a struggle to do so. So in conclusion, we can say that this analysis mostly depends on the perspective and who is classifying the event. So it is really subjective, and we can face a lot of challenges because of the keywords. Sometimes can be a little bit ambiguous, or the reports, or sometimes it can be very vague. So those are some challenges we kind of need to address. So something else is that the National Weather Service could standardize the flash flood impact, and we could also add a flash flood severity index column to the event, because this was outside, this FSI was created outside the National Weather Service, and this is analogous to the tornado reports in like the EF scale that is used for the report. So the IBW category would kind of match with that scale. So because it's a post-event analysis. And also we will need to conduct more IBW studies to increase the confidence in classification and the keywords. So we can come up with a methodology. So if someone else is classifying the events, we won't go through that struggling and uncertainty and where to put the different keywords and which category choose. And so for the future work, we can expand this to other weather forecast offices around the country, because this project was only for the NOAA forecast office. And we could also analyze the events one by one. Instead of only taking the daily max, we could analyze the 671 events. And also something that could be very useful is try to correlate the impact-based warning classification with different National Weather Service tools, such as the MRMS or the Flash tool or the FMP. So this could be very useful to see what comes up if we do that. So thank you for your attention.
Thank you. Let's go ahead and give her a nice round of applause. Awesome talk. Once again, go ahead and type a Q in the chat if you have any questions, and feel free to either leave your screen sharing just in case somebody has any questions, or close it if it's hurting your connection. But while we wait for another question, we have lots of awesome chat going on, congratulating. I do have a quick question. I know this isn't anything that you particularly looked into, but given your history of being bilingual, how do you think that this is going to be important when also translating these messages in Spanish?
So for me, it is very important to try to communicate this to the bilingual community, because in the past, we had some struggles doing that, and a lot of Hispanic people have been affected by events like this. So that is something that we need to do, like, urgently. It is a problem we need to address.
Yeah, absolutely. Alex had the same question, so she said I stole hers. Ben Schenkel has a question, so Ben, you can go ahead and unmute yourself.
Interesting talk, America. It was really good. I just had a question for you, specifically with the road street example that you gave. Do you have any suggestions about specific details or improvements that could be made to that, like being more detailed about the type of flooding, or what suggestions do you think you have for that?
Yeah, I think that would be a great suggestion, just to kind of try to, in the 1 year or something, add to let people know that it's like a dangerous situation, even though the wireless emergency alerts let you know when it's a considerable or catastrophic situation. But sometimes the language is a little vague, so kind of try to improve that so people would get a better understanding of it.
Thank you.
Awesome. And great job. Harold has a question as well, /comment. So go ahead and unmute yourself, Harold.
Yeah, I just want to point out that this road street ambiguity affects the Weather Service in other ways too. 'Cause it's the same thing with wind damage. You know, if the Weather Service can classify something as tree limb down, and you know, it's a whole lot different when that little 1-inch diameter tree limb comes down and when the 2-foot tree limb comes down. And so that's actually, in some senses, Weather Service has a problem with this on a lot of their products when they try to talk about impacts that, you know, we use really ambiguous terminology. And so you're running up against something that if you decide to in this field doing that kind of thing, you can knock yourself against the wall all the time in different areas. So, but yeah, that makes the evaluation just so challenging, unfortunately.
Yeah, but there's that much more important too, because it's so challenging. So, and especially like, you know, we were saying earlier with the bilingual community, especially, there's work going on at OU about that, looking at different SPC categories and how they translate in Spanish. Unrelated, but just thought I'd point that out since we're on the same topic. But if we don't have any more questions coming in through the chat, we can go ahead and give America a big round of applause. And I will go ahead and turn it over to Kelsey for our next speaker.
All right, so our next speaker and the last one for today is Henry Santer. Henry, you want to go ahead and pull your presentation up? Okay, Henry's going to be presenting on the uncertainty estimation of MRMS V12 radar QPE. Henry, you can go ahead whenever you're ready.
All right, is my presentation showing?
Yes, we can see it.
Awesome. So again, my name is Henry, and I'm going to be talking about understanding uncertainty for a new multi-radar multi-sensor, or MRMS, radar product. My research has been with Dr. Heather Grams and supported by the NSF. This is just a quick roadmap of where we're going to go in this talk, and we're going to start with some background on the data I've been working with. So quantitative precipitation estimation, or QPE, allows us to do a whole lot of things: generate flood warnings, verify our forecasts, and model how water moves and where it goes. But whenever we generate a QPE, it has some uncertainty associated with it. So, and understanding the sources and the significances of those different sources of error is important. And just as important is understanding how that error structure changes from one generation of QPE to the next. And that's what my focus has been on. The MRMS system takes in input from an array of different sources, from gauge data, from the NexRad radar, from model and satellite information as well. And it outputs high resolution, 1 kilometer in space and 2 minutes in time, information about hail, lightning, different metadata, and precipitation estimation, which again is what our focus has been. The two radar products that I'm going to be talking about in particular are called Q3RAD, which is the QPE that came with the initial operating version of MRMS, and Q3EVAP, which is the new product. Q3EVAP is novel because it uses rainfall relationships based on specific attenuation, which is denoted by A, and applies an evaporation correction. Studies in the past have shown that R of A relationships have had a higher linearity with rainfall than other variables, and have been immune to partial blockage of the radar beam. R of A methods don't always work though, particularly when there's hail or mixed phase precipitation in the atmosphere. So Q3EVAP is a synthetic product. It uses R of A methods when it can, and then when it is not sure, essentially, it will use R of KDP methods based on specific differential phase, and in or above the melting layer, it'll actually revert back to Q3RAD. After that synthetic product is created, the evaporation correction is applied to reduce false precipitation echoes from Virga. And then just a bit about Q3RAD. Q3RAD uses only R of Z relationships based on radar reflectivity, and it uses a choice of different relationships based on a precipitation flag that MRMS assigns. So if rain is convective or warm stratiform, things like that. The MRMS Radar Quality Index product describes radar uncertainty at some given point or observation based on the distance from the radar and a bit on partial beam blockage. RQI is assigned on a scale from 0 to 1, and generally low RQI will suggest that the information that we're getting is coming from higher radar beam heights. The data that I've actually been working with has been a collection of hourly rain gauge accumulations paired with QPEs from Q3 EVAP and Q3 RAD. The collection period was over August of 2018 to February of 2020. And because we've been using the gauge accumulations as our reference values, we've been assuming that they're accurately reflecting the true rain rate. Next, we're going to move on to a regional analysis of both of the products. Here we have the mean differences between both QPEs and the gauge accumulation. Red means we are underestimating rainfall, and blue means we're overestimating. The easiest takeaway to see probably is that Q3 RAD has more significant overestimation over the central US and the Great Plains, and that Q3 EVAP does seem to mitigate that. But past that, it seems that Q3 EVAP is actually lowering measured rain rates everywhere. So we have more widespread underestimation under Q3 EVAP, and especially in the West, some more significant underestimation. We're attributing this to the evaporation correction, lowering rainfall rates across the board. And looking at the mean differences for the entire data set, we have that corroborated a bit. We see that Q3 EVAP still has a small overestimation bias, but is smaller than Q3 RADs. On the left here, we have the same mean difference plot for Q3 EVAP, and on the right, we have the average RQI over the course of the study. What we see is that there's a pretty good correlation between areas of low radar quality and areas of underestimation. And past that, areas with really low RQI tend to give us more significant underestimation again. We are attributing this to the evaporation correction overcorrecting based on information that it gets at high beam heights and lowering rain rates past or further lowering rain rates. On the left here, we have the correlation coefficient between Q3 EVAP and the gauge accumulations. And on the right, we have the correlation difference between Q3 EVAP and Q3 RAD. So green here means that Q3 EVAP is better correlated with the gauge-based rainfall than Q3 RAD. And we see that that seems to be the case over almost all of the US, with the only exceptions being some areas in the Rocky Mountains and the Cascades, which are also areas of lower radar quality. Looking at the actual values for the correlation, we see pretty strong correlation in the central and eastern US, and somewhat less strong correlations toward the west, and again, particularly low in the Rockies, or in areas where we've had lower RQI. Here we have similar plots, but for the root mean square error. Green here on the right plot means that Q3 EVAP is a better fit for the gauge-based rainfall rates than Q3 RAD. We see that that seems to be the case over the central and southern US, but that there's not a significant RMSE difference in the rest of the country. One thing we still have to understand a little bit better is that we see some decrease in performance. Q3 EVAP's root mean square error is greater than Q3 RAD's over some metropolitan areas. As an example, you can see Miami, Dallas, and the DC area on this map, and we're still not quite sure why that is. Next, we're going to move on to error modeling. What we mean by this is we've plotted the differences between the QPEs and the gauge accumulation as function of different environmental variables to understand how they're sensitive, or how that error is sensitive to the different variables. And our data is very heavily skewed towards smaller accumulation values. So to understand how the products behave at higher rain rates, we've actually generated the same plots, but only considering accumulations above 10 millimeters. Starting with RQI, we see that low RQI leads to a more pronounced underestimation bias in Q3 EVAP than Q3 RAD. Again, we think this is because the evaporation correction tends to overcorrect when we already underestimate at low RQI. For higher rain rates, we see that both QPEs behave very similarly at low RQI, and then Q3 EVAP gets a pretty significant increase in performance. It's closer to the true value at higher RQI. Our understanding is that low RQI generally means that we have higher radar beam heights and we are more likely to intersect the melting layer and have Q3 EVAP revert to Q3 RAD, so that the performance difference between Q3 EVAP and Q3 RAD at low radar quality should only really be the evaporation correction. What we see though is that at higher RQI, when we are able to leverage the R of A relationships more often, that Q3 evap does perform better. Next is the height of the melting layer. We see that Q3 rad has a systematic overestimation bias for the full range of melting layer heights, but that both products do tend to overestimate a little bit more past 4,000 meters. At high rain rates, we see a similar phenomenon to what we saw with RQI, where at low melting layer heights, we are more likely to intersect the melting layer and revert to Q3 rad. So we see similar performance for both products at the lower ranges, and then improvement with Q3 evap once we break around 3,000 meters. Next is dew point. Again, we see that systematic overestimation. Both products do overestimate a little bit more past 15 degrees Celsius. At higher rain rates, we see that the Q3 evap residuals get closer around the mid-range of dew point values, but then fall off toward the Q3 rad ones again, which we found interesting. For surface temperature, we see, again, that overestimation bias, but both products do overestimate more at higher temperatures, Q3 rad especially so. And we were pleased to see that that Q3 evap did mitigate that severe overestimation that we got with Q3 rad. For higher rain rates, again, we see this pattern of Q3 evap having better residuals in the mid-ranges, and then Q3 rad tending to, or we see again that Q3 rad tends toward overestimation at high temperatures, which Q3 evap still again is able to mitigate some. Organizing by the gauge accumulation values themselves was interesting to us because we see that for the very lowest gauge accumulation values, we do still have a little bit of overestimation. We have the mean residuals listed here, but that for higher rain weights, the underestimation that we get grows quite quickly. We were still happy to see that Q3 evap's residuals were closer to zero than Q3 rads for the most part, but they were more spread out. And one thing we want to note is that the sample size is quite a bit smaller for the higher rain rates, which we think is why we seem to have a good amount of noise toward the right end of these plots. To understand the error structure with respect to the gauge accumulation a little better, we modified a tool that we made earlier in the summer to answer this question in the top left. When the gauge accumulations land within a given interval, what are the QPEs likely to measure? The bottom right figure here, just for illustration's sake, the green curve shows what the range of Q3 evap values are that we might expect to read when the gauge accumulation is between 45 and 47.5 millimeters. Coming back to the top left figure and moving down to the right, we see that both products behave pretty similarly at the low rain ranges, but that as the rainfall rate increases, we tend to have Q3 evap follow the gauge accumulation more closely, in the sense that the expected value of it tends to be closer, but it is still more spread out than the distribution for Q3 rad. In summary, compared to Q3 rad, Q3 evap is closer to the true rainfall rates in general. It does tend to underestimate more than Q3 rad at lower RQI, but it does a good job both of mitigating the underestimation bias at high rain rates and the overestimation bias at low rain rates that Q3 rad has. We do still see, though, that it is a less good fit than Q3 rad around some major cities and areas of lower RQI. Moving forward, we want to leverage the information from this study to have probabilistic QPE. So given a Q3 evap measurement and environmental information, we want to understand the probability that we'll get different rainfall events and exceed rain rate thresholds and things like that. And we also want to understand how changing our hydrological models and calibrating them to Q3 evap will change and how they will be sensitive to that, since obviously the way that we measure how much rain is in different places will affect how we determine how it moves. That's all. Thank you.
Awesome. Let's give him a nice round of applause. Thank you. Again, if you have a question, go ahead and put the Q in the chat. I have a quick question, though.
Sure.
Have you considered, or have you and your advisors considered limiting your analysis to just like east of the Rockies to try and like isolate errors if it's like actually like the Q3 rad and evap versus all of the other issues that come with the stuff in the West?
So we have one thing that we are interested in, or that we've discussed a little bit, is seeing in particular how the evaporation correction fares east and west of the US, or I'm sorry, of the Rockies. It's possible that not applying the evaporation correction in some regions might actually be more beneficial to us because of that underestimation we were seeing at lower radar quality, which we get more in the west. So it is something we're interested in, but we haven't really looked at it yet.
Yeah, awesome. Getting some great feedback in the chat as well. Remember, if you have a question, go ahead and type a Q in your chat. All right, we have a question from Harold. Go ahead and unmute yourself.
Sure. Okay, Henry, this is potentially ridiculously cool stuff you've done. And in particular, there's a public policy issue involved here. In 2017, NOAA was given the responsibility under the Weather Act to produce a report on radar gaps and their impacts on forecasting, and they're only 3 years late getting the report finished. But if they came to you now and said, what could you tell us about the impact of radar gaps on our ability to understand what's going on based on your results, what would you tell them?
I'd probably say that radar gaps, since they do mean that we have more observations that are further from radar sites, which means that we're observing higher up in the atmosphere, do tend to give us more underestimation. Do tend to give us more underestimation than we otherwise would have, so that there's potentially a risk associated with having radar gaps of not predicting enough rainfall and potentially, having a human safety risk there.
Thank you. And just to be precise, the chances of them asking you that question, asking anybody that question, are incredibly small.
Awesome. Thank you, Harold. JJ has a question/comment as well. So go ahead and unmute yourself.
Yeah, very, very nice work. I'll admit my master's thesis was looking at some MRMS products in kind of early development back in the mid-90s. And my whole thesis was based on data from one radar in 3 cases. And that was a master's thesis. So, I mean, where students have come along and at an undergraduate level, and it's amazing. It really is. So, and the degree analysis that went into that's really, truly incredible. So, anyhow, hats off to you. I was going to ask, what happens at the higher end, on the rainfall rates, and you answered that. And so, really, the only question I was left with was how to address the RQI issue. Do you have any thoughts? Is putting in little gap filling X-band radars everywhere? I think the key is you've got to get good coverage at low levels. That's kind of the challenge. So that's going to be challenging to satellite sensors. You can't put rain gauges everywhere. So just curious if you had any thoughts about that.
So theoretically, I think it would be great and probably quite useful to have that sort of smaller X-band radar available in, more remote places that we don't cover super well right now. In truth, though, I don't know what the limitations are and how difficult that is in practice. So I don't really know realistically a good answer to addressing that.
Since we have the time, did any of the advisors want to chime in with any of their thoughts on the questions posed by JJ? Just wanting to give that the opportunity. I don't know if Heather is here. I don't see her on my little screen. Okay.
Part of my research is to try to develop satellite-based QPE techniques to try to fill in some of these areas where we don't have good radar coverage. So, and JJ is well aware of this because he was one of my co-collaborators on some past work that I did with that. But the gap filling radars would be definitely helpful in the mountains, but you would need a lot of them. So I think there's a cost issue and getting, who's going to pay for it. But yeah, we would love to have more observations where we don't have them. But for right now, the best we could probably do is satellite and trying to use new machine learning techniques to try to come up with QPE estimations where we just don't have alternate sources of data. And with GOES 1617, that's a really great opportunity. It's just how do we use that information in a way that gets us reasonable QPE near the surface, which is tough.
Yeah, great. Thank you. We have a question from Amanda. So if you can go ahead and unmute yourself.
Of course. First off, Henry, great talk. Thank you so much. This was so interesting. R of A algorithms, I know we're starting to use them more and more. So my question, because I'm not super familiar with them yet, you were explaining R of A algorithms and you said that they struggled when looking at hail. I don't know if I'm saying that correctly. Could you just kind of explain why they would struggle in regions of hail?
In truth, I don't really know the answer to that. Most of my focus has been doing the data analysis side on this project. So I wanted to understand what the implications of having different methods and looking at or focusing on different radar variables would be, but I don't know the details of why RFA methods are what we have decided is the good thing to look at right now, and also why they have the limitations that they do.
That's fine. I don't know the answer either, so I guess I've got some reading for this afternoon. Thank you.
I can try to take a stab at it. Specific attenuation uses some dual pole moments. It uses differential phase, and it also uses reflectivity to try to estimate how much the different radar beams are attenuated by liquid precip. So radar, the energy we send out from radars is attenuated differently depending on the phase of the liquid it's going through. So if you have all raindrops, it'll attenuate in a way that we can sort of model with this specific attenuation model. Whereas if you have something like ice, grapple, hail, ice takes a lot of different characteristics when you're talking about precip. So it's difficult for us to estimate how a radar beam would attenuate or if it would attenuate much, because when you're talking about light snow, it really doesn't attenuate much at all. So just the attenuation characteristics are different when you're talking about ice, and it's hard for us to model. So really the specific attenuation that's been developed so far is really just valid and not ice.
Thank you.
Awesome. If we don't have any other questions for Henry, we can go ahead and give all of our speakers today a big round of applause. Everybody did a fantastic job doing this over Zoom, especially great research. This just shows that how awesome research can be done remotely. I feel like this is a prime example to show more national and international collaboration. I'm just going to get on a pedestal here, but I will let Alex and Daphne go ahead and take it away.
Yeah, thank you all for all of your support with our interns and showing up today and listening to these talks. It means so much to all of us, especially this year. Being miles apart, everyone is so lucky and fortunate that we were able to make this happen. We will continue our talks tomorrow at noon, and then again Monday at noon.
Awesome.
Yep, that's all. Have a great day, everyone. See you tomorrow.
Bye.